Hello everyone, welcome back to Max's Math, where we're going to be looking at quiz 4 for Calc 3. If I can adjust my camera right. So, getting started here, problem 1, it asks us to select the statements that must be true, select all that apply. Looking at the first one here, if R is the union of the region, R1 is equal to all this, where X is from 0 to 2 and Y is from 0 to 1, and R2 is the region where X is from 1 to 3 and Y is from 0 to 1, and f of xy is a continuous function. Then we have the double integral of x of across the region R of f of xy is equal to the double integral across the region of R1 f of xy plus R2 f of xy. Now, this one seems like it could be true, but it isn't. The reason it isn't true is if we look at our regions here, we see that the regions are overlapping. R1, 0 to 2, R2 from 1 to 3 in the x direction. We have an overlap from when x is 1 to 2. And for the y's, 0 to 1 and 0 to 1, they overlap completely. So that's why this one isn't false. This region, because of the overlaps, would be greater than this region. In two-dimensional, it would look like if you were to take the integral of, let's say, this graph here, that would be all the area here, right? Which would be equivalent to if you take the integral of this side plus the integral of this side, right? But here, since it overlaps, what ends up happening is that here's our little function, and we would be taking like the integral from, let's say, here to here, so all this, and adding it from the integral from here to here, so all this, and because of that overlap, we overestimate the real integral. So this makes this one not true. Secondly, curves of the form y is equal to g of x form part of the boundaries of a type 1 region in R2. So this one is true, and the reason why it's true is a matter of definitions. In a type 1 region, you have your x's as a locked value, and then your y's vary. And that's exactly what this is here. This is just a regular y is equal to f of x function, so that's perfectly fine. Secondly, r dr d theta is the total area enclosed by the region D in R2. This one also is true, and it goes back to a matter of definitions. When you're trying to find the total area enclosed by a region, you're going to have to do the double integral of 1 dA, or the double integral of 1 dx dy, but converting it into polar, we'd be getting the double integral of r dr d theta. So that works perfectly. There's a 1 here, but the 1 carries out through and multiplies. The reason there's an extra r here is a matter of definition for when we're deriving the whole function and all that. I did the work right over here if you want to take a look at that. It's a whole bunch, but trust me, it works out. The last one here, D, to find the average value of a continuous function f of xy in R3 over a closed and bounded region D, one should calculate the volume of f over D, then multiply by the area of D. This one is almost right. The way you actually have to do this is you have to divide by the area of D. If you want to find the average value, like let's pretend you're just wanting to find the average, you would add up all your numbers and then divide by the number of numbers, right? You wouldn't multiply. Same logic over here works exactly the same. So looking at E here, for every integral function f of xy, there exists v, lowercase v and uppercase v, such that lowercase v is less than or equal to the integral and uppercase v is greater than the integral. Now this one is true. This one kind of goes back to the sandwich theorem and all that, where if we're taking the integral of a function, we know that there could be a minimum bound, which is the integral of the very least value of the function, so all this here, and a maximum bound, which is the integral from the peak value of the function. So it'd be from up here all the way down, all that area. This is just saying this in 3 dimensions, which the logic still applies exactly the same. That we know the function has to be at least this much in terms of area, and at most this much in terms of area, or over here. So that one's true also. Now, due to the instructions of these, we only have to do one on the backside, and I decided to do the integral one here because I have a difficult time evaluating integrals. So, if we're taking a look at this integral, we get a choice here. We could integrate this dx dy or dy dx. Either way, works out the same. Since the x's and y's are separate, we could write this as 2 separate integrals. So, simplifying this a little bit, it'll go down to the integral of e to the negative x plus 5 dx times the integral of 1 over 1 plus y squared dy. Now, to integrate this, it becomes pretty straightforward. The integral of this, simple chain rule and all that, u sub, you could do u is equal to negative x plus 5 and all that, or simply negative e to the negative x plus 5. Now we need our bounds. What are our bounds? Evaluate the integral where r is in the first quadrant. I missed that part. First quadrant. So what the first quadrant means is of your regular plane here, this here is the first quadrant. So x is going from 0 to infinity, and y is going from 0 to infinity. Well, that shouldn't be there, but. So we have to bound this here from 0 to infinity. So plugging in infinity, this becomes a limit here, and this should be saying the limit of negative e 1 over negative e to the power of x plus 5. Because we have this negative exponent here, it writes down and flips down to this. If you plug in infinity here, this is going to be 1 over a very large number. So 1 over a very large number over at infinity, which technically isn't right, but we could think of that simply as 0, because 1 over 10 is small, 1 over 100 is smaller, 1 over 1,000 is even smaller, so keep extending that logic to 1 over infinity, you get 0. So here we're at 0 minus, we plug in 0 for our bounds. For 0 here, we're going to be getting negative x plus 5, negative 0 plus 5, which just goes to 5, so be negative e to the power of 5, so minus e to the power of 5, so this just comes out to e to the power of 5. We have to multiply this by our integral of y here, which this integral, if you remember your arctangent integrals and derivatives, all that, simply comes out to tangent of negative 1 evaluated from 0 to infinity, because remember I was asking for us to evaluate in the first quadrant. So this integral here, we start at tangent of infinity. That might seem like difficult to do, but it's really not. If you recall what the tangent graph looks like, the arctangent graph, if you were to graph it, it looks something like this, where there's asymptotes at pi over 2 and negative pi over 2. So as arctangent goes to infinity, it goes to pi over 2. And subtract that from the arctangent of 0. Where is tangent 0? At 0, so minus 0. So plugging everything in, we have to multiply these two. So we take e to the 5 multiplied by pi over 2. And, well, looking at our answer choice, we get D here. So the math all works out perfectly and everyone's happy. Thanks for watching. That's quiz 4.